Hi, I'm Daniela Bonus from Math3D, and for this video we will tackle Chapter 7, Confidence and Interval and Sample Size. Exercise 7.1 Number 1. What is the difference between a point estimate and an interval estimate of a parameter? Which is better? Why? So the question is difference between a point estimate and interval estimate of a parameter. So a point estimate gives us a particular value as an estimate of the population parameter, whereas the interval estimation gives us a range value which is likely to contain population parameter. If repeated random sample we will taken from population, the point estimate will be expected to vary from sample to sample. A confidence interval will include a true parameter if repeated in sampling. Neither is better. In practice of an interval, it's more useful. A point estimate is something like, I think they will pay you 10 pesos a year. Should a pretty good? An interval is, I believe they will pay you between 5 and 10 pesos a year. That might tell you that there's a lot of variation. So, if an interval estimate is symmetric, the middle point of ordinary supply is reasonable point estimate, but not necessarily the maximum likelihood estimate. This will generally true for positive quantities like standard deviation. Neither statistic is better than other. Everything depends on the purpose. Mind you, any and all seems to be subject to some outlandish interpretation. So that's it.
Good day everyone, I'm Maureen Pidades from BS Ed Math 3B and I was assigned to answer one of the exercises in 7.2 that is all about confidence intervals. Here is the problem. In number 9, find each A. Z sub alpha over 2 for the 99% confidence interval. B. Z sub alpha over 2 for the 98% confidence interval. C. Z sub alpha over 2 for the 95% confidence interval. D. Z sub alpha over 2 for the 90% confidence interval. And E. Z sub alpha over 2 for the 94% confidence interval. Let's start with A. Z sub alpha over 2 for the 99% confidence interval. By using the normal curve distribution between positive Z and negative Z, the area of this region based on confidence level, this is 0.99. So the remaining 1% is divided by the left and the right of our Z. 1 minus 0.99 is equal to 0.01. That is the value of our alpha. Alpha over 2 is equal to 0.01 over 2 is equal to 0.005. 0.99 plus 0.005 is equal to 0.995. By looking the table of Z value, we will find the location of 0.995. That is equivalent to 2.58. B. Z sub alpha over 2 for the 98% confidence interval. Using the normal distribution curve between positive Z and negative Z, the area of this region based on confidence level, this is 0.98. The remaining 2% is divided again from left to the right of our Z. 1 minus 0.98 is equal to 0.02. 0.02 divided by 2 is equal to 0.01. 0.98 plus 0.01 is equal to 0.99. By using again the table of Z-score, we will find the location of 0.99 and that is 2.33. See? Z sub alpha over 2 for the 95% confidence interval. By using the normal distribution curve between positive Z and negative Z, the area of this region Based on confidence level, this is 0.95. So the remaining 5% is divided by the left and right of our z. 1 minus 0.95 is equal to 0.05. That is the value of our alpha. 0.05 over 2 is equal to 0.025. So that is the value of our left and right z. 0.95 plus 0.025 is equal to 0.975. Using again the table, we will look for the location of 0.975, and that is equivalent to 1.96. D, Z sub alpha over 2 for the 90% confidence interval. By using the normal curve distribution between positive Z and negative Z, the area of this region, based on confidence level, this is 0.90. So the remaining 10% is divided by the two parts from the left and the right of Z. 1 minus 0.90 is equal to 0.10. That is the value again of our alpha. 0.10 over 2 is equal to 0.05. That is the value of the left and the right of our z. 0.90 plus 0.05 is equal to 0.95. By looking again to our z-score table, we will find the location of 0.95. So that is equivalent to 1.65. And E, Z sub alpha over 2 for the 94% confidence interval. By using again the normal distribution curve between positive Z and negative Z, the area of this region, based on confidence level, this is 0.94. So the remaining 6% is divided again by the left and the right side of our Z. 1 minus 0.94 is equal to 0.06. That is the value of our alpha. 0.06 over 2 is equal to 0.03. That is the value of our left and right Z. 0.94 plus 0.03 is equal to 0.97. By looking again by the z-score table, we will look for the location of 0.97. That is equivalent to 1.88. That's all. Thank you and God bless.
Good day everyone, I'm John Cyrus Picabras from VS EdMath 3B, and here we have another problem. Unmarried Americans. Nearly one half of Americans aged 25 to 29 are unmarried. How large a sample is necessary to estimate the true portion of unmarried Americans in this age group within 2.5 percentage points with 90% confidence? So, first we need to list our given. We have our P is equal to 0.5. Our Q is equal to 1 minus 0.5 is equal to 0.5. Then we have our Z is equal to 1.64. Then our E, which is 0.025. Since we have this given, we can now substitute it in in the formula for the minimum sample, which is N is equal to PQ Z over E square. So N is equal to 0.5, Q is 0.5, we have our Z, which is 1.64 over our E, 0.025 square. This is equal to 0.25 Then 1.64 over 0.025 is 65.6 square. Then this should be equal to 0.25 multiplied by 4,303.36. Then n is equal to 0.25 multiplied by 4,303.36 is equal to 1,075.84. So with a 90% confidence, a minimum sample of 1,075 is necessary to estimate the proportion of unmarried 25 to 29 Americans. That's all. Thank you.
Hi, good day. I'm Danielle Bonas from Math 3B, and in this video we'll tackle exercise 7.1, number 25. If the variance of a national accounting examination is 900, how large a sample is needed to estimate the true mean score with 5 points with 99% confidence? So we have our given, our variance is 900, and when you square the 900, that is equal to 30, and the 30 is now our standard deviation. And we also have our E, or the maximum error of estimate, which is 5, and of course the Z alpha over 2, which is equal to 2.576. Now you're wondering where did our Z alpha over 2 came from? It came from the given of 99% confident. So let's look at this table. The confident is 99, and we have to find the Z alpha over 2. So the confident level 99% is equal to the Z alpha over 2, 2.576. So now we have this formula, or the formula for minimum sample size needed for interval estimate of population mean. So we just have to substitute the given. So our Z is 2.576 multiplied by 30 over maximum error of estimate raised to 2. So that is equal to 238.887936, or our sample size is 239. That's all. Thank you.